We will continue to learn the knowledge of sinusoidal alternating current today. We have studied 3 elements of sinusoidal alternating current last class. In this lesson, we will study phase difference of sinusoidal alternating current with the same frequency and the representation of alternating current. What is the phase difference? It refers to the difference in phase angle, or initial phase between 2 sine quantities with the same frequency. This is known as the phase difference. Here is the sine voltage and the sinusoidal current. Their expressions are as follows. U equals UM sine of omega t plus phi u. I equals Im sine of omega t plus phi I. Through observation, we found that both have the same frequency and satisfy the condition of phase difference. In the same sinusoidal alternating current circuit, the frequency of AC voltage U and alternating current I are the same. But the initial phases are not necessarily the same. This means that these 2 sine quantities have time periods of positive value that occur at different times, with slightly different paces. Therefore, we can conclude that there is a phase difference between them, as shown in waveform diagram 3-1, as can be seen from the figure. Current and voltage are alternating currents that change according to sinusoidal laws with the same period, but different initial phases. Their initial phases are phi u and phi I respectively. Their phase difference between them is obtained by subtracting the phase of AC current from the phase of AC voltage. Since the voltage and current frequencies are the same, the final phase difference is equal to the difference between their initial phases. The absolute value of phase difference can't exceed 180 degrees or pi. The phase relationship between 2 sinusoidal alternating currents with the same frequency can be categorized into the following 5 scenarios. 1. When phi ui greater than 0. That is, phi u greater than phi I. It indicates a leading phase relationship of the voltage U with respect to the current I by an angle of phi ui. In other words, the phase of current I lags behind the phase of the voltage U by an angle of ui. Second, when phi ui less than 0, namely phi u less than phi I, it indicates a lagging phase relationship of the voltage U with respect to the current I by an angle of phi ui. Third, when phi ui equals to 0, it represents a sinusoidal AC voltage U that has the same phase as the sinusoidal AC current I. We call this being in phase. Fourth, when phi ui equals plus or minus pi, or plus or minus 180 degrees, it represents a sinusoidal AC voltage U that has the opposite phase to the sinusoidal AC current I. We call this being antiphase. Fifth, when phi ui equals plus or minus pi over 2 or plus or minus 90 degrees, it represents a sinusoidal AC voltage U that is orthogonal to sinusoidal AC current I. Pay attention to the fact that two sine quantities with different frequencies cannot be compared in terms of phase. Next, let's learn about the representation methods of sine quantities. As mentioned above, sinusoidal quantities can be expressed using trigonometrical functions, which are mathematical expressions. They can also be represented using waveform diagrams. The former is the basic representation method, but the calculation is complicated. The latter is intuitive and visual, but may not provide accurate results in terms of calculations. In order to facilitate the analysis and calculation of sinusoidal circuits, the phasor method is commonly used to express sine quantities. Sinusoidal alternating currents can be represented by amplitude phasors or effective value phasors. Usually, effective value phasors are used to represent them. Phasors are represented by capital letters with a dot above. If the maximum value is used as the length of phasor, and the initial phase is used to the amplitude angle of the phasor, it is called the maximum value phasor. As shown in Figure 3.2.2, all three phasors are maximum phasors. Another representation of sine phasor is the effective value phasor. If you use the effective value as the length of the phasor and also use the initial phase as the amplitude angle of the phasor, as shown in Figure 3.2.3. All phasors are effective value phasors. The diagram of phasors on the complex plane. It should be noted that only sine can be expressed by phasor, and phasors cannot represent non-sinusoidal periodic quantities. Only sine quantities with the same frequency can be compared and calculated on the same phasor diagram. The knowledge points of this lesson have been covered. Finally, I left 2 questions for you. See you next class.